this is the Chapter 5C assignment video, and this is the assignment that has to do with the central limit theorem. So let's look at the first problem. The first problem states that the mean temperature in Knoxville, Tennessee in the month of January between 1872 and 2015 was 38.6 degrees, but the distribution is unknown. Assume the standard deviation is 10 degrees. We take a sample of n equals 49. Find the following probability. So we're trying to figure out what is the probability that the average temperature of those 49 samples that we took would be less than 40. Now, because we have a sample size that's greater than 30, we can apply what we know about these normal distributions to come up with our probabilities. However, if the sample size is not at least 30 and we don't know that the population or that the distribution is normal, we are not able to do this. But since we, even though we don't know how the distribution looks, we don't know that it's a normal distribution, we have a large enough sample size where we can use the central limit theorem. So what the central limit theorem tells us is that when we take the sample of 49 temperatures, what we know is that the mean of the sample is going to be equal to the mean of the original population, which was the 38.6. Now, the standard deviation we have to adjust, and as the sample size gets larger, the distribution gets more narrow, which means the standard deviation changes a little bit, the variation changes. So what we're going to do is we're going to get what the standard deviation of our sample means is going to be. So we have the sample of 49 different temperatures. So the standard deviation of the original population was the standard deviation was 10. But we have to adjust that a little bit because we're going to divide by the square root of 49. That's our sample size. When we do that, that gives us the standard deviation of our sample means, which if you do that math, dividing that out, is 1.43. So now we have some information to work with when we're going to make these, finding these probabilities. Okay, so we have a mean and a standard deviation. Now for this particular problem, we are going to work with z-scores and then take what we find about our z-scores to figure out some probabilities about the actual temperatures. So we need to convert this 40 degrees that we're interested in. We need to convert this 40 degrees to a z-score. So I'm going to come over here, I'm going to squeeze this in right here. The z-score for 40 degrees is just taking that temperature, that value, minus the mean, 38.6, divided by the standard deviation. Now this is not the population standard deviation that was given, that was 10, but it's this adjusted standard deviation. We use the central limit theorem to figure out what the standard deviation is going to be of our sample means. So we're going to use the 1.43 here to get the z-score that we need. So doing that math, we get 0.98. So going back to our probability statement, the probability that our sample means, so that the mean of the 49 temperatures that we got, so the probability that the sample mean of those temperatures is going to be less than 40 is going to be the same thing of what the probability of getting a z-score less than 0.98 would be. So we can go to our standard normal calculator and StatCrunch to figure that out. So stat calculator normal, and this is our standard normal. We're working with z-scores, so when we're working with z-scores we keep this 0 and this 1, and we will want to know the probability, and this says x but we can't change that, but the probability that a z-score would be less than or equal to 0.98, and we get 83%. Actually that would round to 84, so let's draw out our normal models. This would be the distribution of our z-scores, and this will be the distribution of the temperatures. So we have a mean of 0. And we have a z-score up here. It's above average somewhere of 0.98. So when we put this into our normal calculator, it told us that this area here, my pen is going on me, that area, let me switch pens, is the 0.84. So the probability of getting a z-score less than 0.98 would be 84%, so 0.84. So what we can also say over here on our normal model, the average temperatures that we had in our population was 38.6. And we were wanting to know what's the probability of getting a sample of 49 temperatures, and that the average of those 49 would be 40 degrees. So that's going to be the same as this probability that we computed over here using z-scores. So it's going to be the same. This is going to be 84%. So I wanted to show you, this is kind of an intermediate step that if we're using StatCrunch, sometimes we can, or not sometimes, we can skip this step. So what we could have done was we could have gone over here and put the mean of the sample, the mean of the 49 that we got the 49 temperature samples, and by the central limit theorem, we know that the mean of those samples, the 49, is going to be the same as the mean of our population, which was 38.6. So that doesn't change. But what does change with this problem, this is using the central limit theorem. We don't know that we have a normal distribution, but we're taking a sample of 49. So we're not looking at the probability of just taking one temperature, right? We are looking at the probability of getting 49 different samples, 49 different temperatures, and seeing what the average temperature would be. So that's why we need to apply the central limit theorem. We are looking at a sample, not just one temperature, but a sample of temperatures, and then looking at that mean. So the mean stays the same for that sample, but jump down here, we have to calculate a new standard deviation. And so the way that's done, just remember we took the given standard deviation of 10 for the population, divide by the square root of our sample size, which was 49. And so this is where the 1.43 goes in, goes right there. Then we would just change this to 40, and we get the same thing. There's the 84%. So we would say that the probability of the sample of 49 temperatures would have a mean of 40 is 84%, or 0.84. Going to the next problem, this is a problem that has to do with a roller coaster. So a roller coaster is being designed that will accommodate 58 riders. The maximum weight the roller coaster can hold safely is 12,000 pounds. So according to the National Health Statistic reports, we know that the weight of U.S. adult men is an average of 194 pounds with a standard deviation of 68. And the weights of U.S. adult women have a mean or average weight of 164 pounds with a standard deviation of 77. So we've got a lot of information going on here. But what the problem's getting at is we're trying to figure out if we put those 58 riders on that roller coaster, is it going to be safe? Okay, so we need to figure out some things here. So if there are the 58 people that are going on that roller coaster, and the total weight cannot exceed 12,000 pounds, what would the average weight be for each rider? So what we would do is we would take the 12,000 pounds and divide that up by the 58 riders. And so that would be that each rider would weigh about 207 pounds. So let's see how this relates to what might really happen. So 58 random people will be getting on the roller coaster. And so we're going to assume the worst case scenario. We're going to assume that they're all men. So this information about women, we're not going to really use that. We're just going to consider the worst case scenario that it was 58 men on the roller coaster. So we have a sample. We're not just looking at the probability of one man being greater than the 207 pounds. We're looking at what's the probability that the average of all 58 would be greater than 207 pounds. So our probability statement that we're looking at is what's the probability that our sample means, that the mean of our sample is going to be greater than or equal to 207 pounds. So by the central limit theorem, we know some things about our sample. We know that the mean of our sample is the same as the mean of the original population, which we know to be 194 pounds. We also know by the central limit theorem that the standard deviation of our sample is equal to the standard deviation of the original population, which was 68, and we divide that by the square root of our sample size. So our sample is 58. So if we do the math here, that means the standard deviation of our sample is 8.9. So we can plug this into StatCrunch and figure out what's the probability that if we have the 58 men, what's the probability that we will exceed the maximum safe weight. So this is what we need to consider. So the mean or the average weight of a man is 194 pounds. But since we're looking at the sample of 58 riders, the standard deviation had to be adjusted a little bit by the central limit theorem, and that's the 8.9 that we got right here. And then we want to know what's the probability, this should actually be X bar, that the mean of our sample is going to be greater than the 207 pounds. And it looks like there's a 7% chance, so 0.07, that the maximum weight could be exceeded by those 58 men getting on that roller coaster. So we would say there is a 7% probability that the maximum safe weight will be exceeded. Moving on to problem number 3. Actually, let's go back. I didn't fill out the normal model, so let's just take a look at that so we have a visual of what's going on. We have it over here, but I just like you guys to get in the habit of putting here that the average weight of men is 194. We were up here at 207, and we wanted to know what's the probability that the average weight of the 58 men would exceed the 207. And we got in over there in StatCrunch. This right here was 0.07. All right, now let's move on. Number 3. The shape of the distribution of the time required to get an oil change at a 10-minute oil change facility is unknown. However, records indicate that the mean time for an oil change is 12.2 minutes, and the standard deviation for the oil change time is 2.8 minutes. So the first question asks, to compute probabilities regarding the sample mean using the normal model, what size would be required? So you need to at least have a sample size greater than 30, because we don't know the shape of this distribution. We don't know that this is a normally distributed distribution of this data here. So we've collected data on the average time to change oil, and it turned out to be 12.2 minutes with the standard deviation, but we don't know for sure the shape of this distribution. Is it normal? Is it right skewed or left skewed? But by the central limit theorem, as long as we have a sample size greater than 30, we can apply what we know about the normal distribution to figure out these probabilities. So we are going to look at the next part of the question, which says, what is the probability that a random sample of n equals 40? So that would be 40 oil changes, that it results in a sample mean time of less than 10 minutes. So we can do this because we have a sample size greater than 30. So what is the probability that the mean of our sample would be greater or less than 10 minutes? So this, remember, they advertise to be a 10-minute oil change facility. So we're trying to figure out what's the probability that if we took 40 different oil changes and we measured how long it took for those 40 oil changes, what's the probability if we averaged all those out that it would be less than 10 minutes? So let's draw our normal model. We know we have the mean of 12.2, and we need to compute the standard deviation. Now, since we're not just talking about the probability of one oil change taking less than 10 minutes, we're talking about a sample of 40 oil changes that the mean time would be less than 10 minutes. So we have to use the central limit theorem and adjust our standard deviation. So the standard deviation of our sample mean is going to be equal to the standard deviation of our population, which was the 2.8, divided by the square root of our sample size, which was 40. So if you do this math here, divide that out, you get 0.44. And we know that the mean of the sample of 40, that the mean of our samples is the same as the mean of the population, which was 12.2. So we're going to use these two numbers when we go over to StatCrunch with our normal calculator to figure out this probability. So we are looking at the average of 12.2 minutes, 12.2 minutes to change the oil, and the standard deviation that we're using by the central limit theorem is 0.44. So we adjusted it there. So the probability that the time to change the oil is going to be less than, less than 10 minutes is, oh, that's not very good. It's almost 0. So this would be 0.000000029. So it's almost 0. So we would say the probability that the average, or mean, maybe I should say mean, that the mean oil change time of the sample of 40 would be less than 10 minutes is 10 minutes will be less than 10 minutes is almost 0. All right, the last problem, number 4. So we are told that the average or the mean ATM withdrawal is $65. Assume the standard deviation for the withdrawal is $34. Do you think that the variable ATM withdrawal is normally distributed? If not, what shape would you expect to have? So what I'm asking here is, would you think that the ATM withdrawal amount, if we looked at all those amounts and we put them, we made a graph of them, or we made a histogram or a distribution of those withdrawals, what do you think? Do you think it would be normal, or there'd be an average and you'd have as many below as above average? Or do you think you'd have a few small amounts, but then you'd have most people making larger amounts? Or do you think maybe most people make small withdrawals and then there's a few that make large? So really this is, could depend on lots of different things, depending on the area maybe that the ATM is located. So it's really hard to say. So really we don't really know if this would be normally distributed or not. So we have to consider our sample size, whether or not we can use this normal model to figure out probabilities. So in part B, we're taking a sample of 48, so that is greater than 30. So we can apply the central limit theorem here and use our normal model to figure probabilities. So in our random sample of 48, using the central limit theorem, the mean of our samples is going to be equal to the mean of the population, which was $65. The standard deviation of our sample is going to be the population standard deviation, which was $34, divided by the square root of our sample size. So the standard deviation that we're going to be working with when we go to our normal model is going to be 4.9. Part C, so we're asked to find what is the probability of obtaining a sample mean withdrawal amount between $68 and $72. Let's draw the normal model. We know that the average is $65, and we're interested in what is the probability that would be between 68 and 72. So 68 was up here somewhere, and 72 is up here somewhere. This is not to scale, but just to give us a visual of where we're looking and where we're going. We're looking at this area that's in between. That's going to be our probability. So this is a between problem over here in StatCrunch. Let me move up a little bit. Here we go. So this is what we're looking. This is our normal model. Here's the mean, and we're looking at this area in between here. Going to StatCrunch, I need to switch to between, and let's enter the mean. So we were told the mean was $65, and we have to use our adjusted standard deviation that we adjusted right here of 4.9. And we are interested in the probability of getting withdrawal amount between $68 and $72. And that area is 0.19. So we shall say, let me write this a little bit differently, that the probability of withdrawal amount being between 68 and 72, that the average withdrawal will be between 68 and 72, the probability is 0.19. So writing that out in words, we would say the probability that a sample of 48 ATM withdrawals is between I would say that the sample of ATM withdrawals would have a mean. That's not exactly right. That the probability that a sample of 48 ATM withdrawals would have a mean withdrawal between 68 and $72 is 0.19 or 19%.